What's that? Oh, I see.
Oh, for real? Why does she make everything so negative? Why would you wish she's in there?
Well,
You're
all right.
responsible for everything.
So the whole idea. Oh yes.
Do you have any more of the handouts?
This one.
The one you just handed out, no, on Monday.
Oh yeah. This I have. I don't have any more of these for some reason. Have y'all seen that? You need another one?
That's very smart.
Anyone else?
Writing in the back. You have a hex, you have a tie or a 6. Or 7.
Cool. So I'll tell you what. We'll recreate the first few. We already did this before, but just to remind ourselves how this works. Click over here. Maybe I'll put. Let's do. All right. Rah. All right, so you got the Z-score stuff over there. Truly multimedia extravaganza. All right, so the very first problem is Z less than 1.51. This chart is just, if you missed last time, this chart is basically empirical rule blown up. So empirical rule, we only know 3 things. The chart fills in everything in the middle. And the way it does that is it realizes that if it just finds the area under the normal curve from basically this starts at negative infinity up. So this is kind of cool. If you watch the Z-score chart, what I'm doing is as I start from negative infinity and I move up, and they say this silly thing here, I don't agree with this. Is there a way to held down at negative 80 Z-scores? Negative 80? That means you're 80 standard deviations below the mean. There's basically nothing there, right? That means you are going up to the knee of Ant-Man or something. I mean, if you're damn tight, it becomes a heights, for example. So as you move up, this collects all the area below where you are. We know from last time that when I look at the Z-score, it tells me the area below that Z-score. So watch, as I move up, I'm collecting more. Now look, why is this not moving very quickly? As I move up, why is this not really changing much at all? Because it's not. So how much stuff is out there? Not much. So I'm just moving along and I'm collecting as big as 0.0003, 002, 0.0003, 003. So it's not really changing. And so and then finally I pick up some more and I pick up some more and I pick up as I move up and I move up and I move up. And of course as my height grows, that means I'm collecting more stuff. So where does this thing change the quickest? Okay, computer. Crap. This thing changes the quickest when I get closer to the middle. Look how quickly it's changing now. As I get closer and closer. Hey, screen. Holy shit, sorry. As I get closer and closer to the middle. This is changing by a decent amount now, right? You see it growing and growing and growing because most of the stuff is in the middle. How's that? So that's how the chart is set up. It says, let's start at negative infinity. And then we'll move, and we'll just keep telling people how much area they've passed so far. And that's, of course, why when you look up positive 3.5, it says, hey, you basically passed everything by. You basically got 100% of it below you. All right, cool. So if I want to know from this paper, it says, what is the probability that Z is less than 1.51? I want this area here. So if I look up 1.51 on the chart, it's going to tell me how much area I've passed to get up there. So when I look up 1.51, 1.51 is here, 0.9345. And that's what we got last time. Cool. Just to remind us how this works. All right, so I think last time we did the first one in number 4. Is that true?
We did do all. Yeah, we did A.
Yeah, we only did part A, right? So let's do part A again, just to remind ourselves how this worked. What goes right in the middle of the picture now? Yeah, 31.64. And I want to know the probability is less than 27.2 minutes spent in a week. So here's 27.2 because it's a real number line, so I just put it where it goes. I want this area here then. I can't look up 27.2 in the chart because it's not on there for one thing, plus it's not a z-score, and that's a z-score chart. Kind of makes sense. So before I can use the chart, I have to make a z-score. Yes, thank you. All right. I don't know. All my classes seem to be like zombies. I'm always wondering, is it me? I am sucking this semester at teaching. My classes have checked out. Shit. Or some of you guys are like, we did this one before, man. So 27.2, my data point minus the mean, divided by the standard deviation. That's the formula for z-score. How many of these fit in here? Because the z-score tells you how many standard deviations there are from your data point to the mean. And what do we get for that? Negative 0.57. We talked about truly rounding the number, right? Don't just cut it. You've got to truly round it. And so if I look up negative 0.57, negative 0.5, 0, 1, 2, 3, 4, 5, 6, 7. Is this the one? 2843? Is that your card? Okay, 2843. And of course, that's exactly what my answer is because the chart tells me the area below, and the question is, what's the area below? So a 28, almost a 28.5% chance that a randomly selected gross 1 student would take less than this much time in a week to find their parking spot. That's the physical situation. All right. So look at number 2. Still put 31.64 in the middle. 53 goes where? Way up here somewhere. And now you start to see the pattern here. If they give me a raw score, I make it into a z-score, and then I look it up. And it's really, what's the right word there? Deceivingly simple. There's a lot of powerful stuff going on in what we're doing. But all I got to do is use that simple formula, use a simple chart, and they got this area. But that is telling me a lot. It's a huge amount of information to know. So how do I change this into a z-score? Good. My data point minus the mean divided by? Sweet. What's that come out to be?
2.73.
2.73? Okay, cool. And then if I look up 2.73, here's 2.70123. 9968. Which kind of makes sense because I'm way the hell up there. So the probability that it's less than that is 0.9. Now I want more than, so what's this going to be? Why did I circle it? What's this part going to be? What's my answer going to be? 1 minus that, so 0.0032. Sweet. I like it. I'll stop there for a second. Is everybody decent with how all of this kind of ties together? We have an ability to create a z-score. What the z-score actually does for me is it strips away all the unnecessary specificness of the problem. I don't care that the mean is 800 million and the standard deviation is 14. I need to know how many steps away is all the data points I'm talking about. And so the z-score is why it's called a standardization, a standard score, is because it standardizes everything in terms of steps. So if my standard deviation was, if my mean was 1 million and my standard deviation is 200,000, I'm like, big data, and I got a little tiny dude, but they still, I can take them both to be 1 step away is here, 2 steps away is there. And that's all that matters, is how many steps have you taken, and that corresponds to the area that's below that, which corresponds to the probabilities. Yes, ma'am.
So if it's more than we need
Yeah, the chart tells you less than. And how do you always find the opposite probability? 1 minus that. Yep. It's the same old thing. If I know the probability less than that is going to be something, the probability more than that is 1 minus. Yeah. Whoa. So then this last dude. Did everybody do this one already? Have you all done this here?
I just did.
You just did it? All right, if you haven't done that yet, go ahead and do it.
Yeah, we did.
Oh, I haven't done it. I haven't done it. I don't follow my own instructions.
I need help with this.
What's up?
I need help with this. So, how do I choose this?
So it's sort of like that part D up there, right?
Yeah, what I 33%.
So why'd we put that line where we did? Because there's got to be 33% in there, right? So where would you put the 14th percentile line? Sure, I love it, because there's point. So above that you would put 0.14. That's the area that's in there. Now can you use that to find none of them? That's below. Above that you would put 0.14. Because below there that would be a z-score. And 0.14 looks like a z-score. It's even. You got to look up the z-score in the. Yeah. So where are you going to look up the 0.14? In the body. I like it, because it's an area. Again.
So it's like, so you're just right, but you don't have.
Oh, I just forgot to write
These are
it.
two separate. I think 1.75. Negative one, yeah, there are areas. 7.5. I'll just put negative 1.
All right, so this is the kind of problem. The only time you have to adjust the answer that you get from the chart is if it's not less than, right? If the question is what's the probability that it's less than something, that's exactly what the chart tells me. The chart tells me less than a z-score. So that if the question is more than, I'm going to do 1 minus. If the question is in between, I've got 2 of them to look up, and then I'm going to subtract to get the area that's left in the middle, right? So how do you change? Just keep doing the pen. What does this become as a z-score? This 15.5. Negative 2.07? Does that sound all right? Okay. I'm trusting you guys. And then what's this become? Negative 1.55? Okay. Crowdsourced problem. So if I look up those two areas, if I look up negative 1.55, I'll get that area. That's way too much. But if I look up the other dude, I get that area, and if I subtract them, I'm left with the area in the middle. That's a beautiful physical situation. You can see physically what's going on in that problem. So when you look up negative 155, what do you get? 0606. So that's this dude, 0606. And then when you look up negative 2.07, 192. Cool. And then when you subtract those, 414, right? 0414, yep. So when you subtract those, you get 0.0414. Which means, yes. Oh, I'm sorry, go ahead. I just wanted to put it next to the question. What is that? You always have to step back and make sure that we're not getting too entrenched in just nothing but pure numbers. Because that's not all that math is, and stats is an example of that. What does that 0.0414 mean? What's the meaning behind that number?
Yeah, the probability that a student, there's a 4% chance that you would pick a Grossman student. Now that's where I stop. There's a much higher chance you would pick a Grossman student because you're surrounded by them. But there's a 4% chance you would randomly pick a Grossman student that did what? Yeah. Took between 15 and a half and 19 and a half minutes to find a parking place. I like it. The gas. So it would be very strange. Would it be unusual to find somebody in that area?
Yes.
Yes, why? The area has less than 5% chance of happening something in there. So that would be an unusual area to find somebody in. Okay, I like it. Cool. So any individual probability, I want to bring this back because I had somebody ask me about this earlier. Remember unlikely versus unusual. Any individual probability can tell you if it's unlikely or likely. But it can't tell you it's unusual. That's not fair. Because the most likely thing could actually be less than 5% chance of happening. What? So that's still unlikely, but it's not unusual. We did the whole thing about the heads. If I flipped the coin 300 times, I think I finally figured out that that's what worked. Flipped the coin 300 times, the highest probability of heads was 4%, 4 point something percent. So it wouldn't be unusual to get 150 heads out of 300 flips of a coin. You wouldn't go, oh my God. Right? I don't know if you'd ever do that anyway. But, so it's not unusual because it's not in an area that's unusual. So the book keeps pounding this point. Find the area of this. Now find the area of this or less. That's the area that you can tell if it's unusual or not, because you're looking to see that where I saw it in that area, is that unusual? So if I see something here, well, that's not an unusual area to be in. But if I see something here, well, that's an unusual area to be in. All right. Whereas this probability might just be 4%. Even though it's the highest freaking thing there, it might just be 4%. But it's not unusual because it's where I expect it to show up. So what about this last freaky little dude?
I know the Z-score.
All right, cool. We're part of the way there.
I got the answer.
Oh, you're like teasing things out. I know this. And I know dudes. So do you notice how this problem is very much like part D up here, right? Then that's what we said. So let me see if you guys. Nobody ever really gets this, but I personally like it. I'm going to keep doing this until somebody understands. In a problem, what normally happens is they'll give you a raw score. You change it into a z-score, and then you look up the percentage. We've done that many times so far, right? We just did it. So if you said no, you're crazy. Now, if they give me the percentage, which is what that problem's doing, it's saying 14% of the people are below that score, right? It's the 14th percentile. If they give me the percent, I got to go this way. I got to change the percent back to a z-score. How the hell do I do that? Z-score chart. What's the z-score chart do? It converts z-scores to areas, probabilities, or it converts probabilities back to z-scores. If I just use it backwards. Anything mathematical basically should be able to go both ways, right? Little judge. And then how do I do this? From a z to an x, or from an x to a z?
Z-score formula.
Z-score formula. It's insane. Woohoo! So the chart goes between these two, and the z-score formula goes between these two. If I start with a raw score, I'll go this way. If I start with an area, percentage, I go that way. All right. So, trying to decide which way to go with this. Well, let's see if somebody has a suggestion. So 14th percentile, where would that go?
A little over 10%.
Here, let me put the mean down there. 31.64, which is a z-score of 0.
15th percentile.
So where would the 14th percentile go? Down there or up there? Down there. Good, because it only has what percentage below it? 14%. But, can't stress this enough. Now, this is the nuts and bolts of working these problems out, right? 14 is a percent. Do not put it underneath, because then your brain, and my brain too, would look at it and say, that's a z-score. 0.14 looks like a z-score. That's a little evil. It's not the problem's fault, it's just the way it is. So you have to be the human in this case and go, I am the human. I know this goes up here. I don't care what it looks like. It's a percentage. So it goes up. I need to figure out what the hell the z-score is so I can work backwards to figure out what the time is. How do I get that z-score for an area of 0.14? Look it up. It's crazy. So normally I look a z-score up here and get the area in the middle. I have the area, so I start in the middle. What's the closest I can get to 0.14?
Negative 1.85.
There we go. Looks like 0.1401. I like that, which, like you said, let's see, negative 1.085.
85. I put 5.
Why'd you do that?
It wasn't exact.
You are a picky man. Because I think 0.1401, that's pretty damn good. Right? But I understand what you're saying, but that's a little too far. If this would have been like 0.142 and this is 0.139 or something, then I would have said yes. Go in the middle, that makes sense. I don't want to call anybody accidentally. So now I can go back and I can say, now I know my z-score is 1.08 negative. That's my z-score now. How do I convert that back into a time? How do I get that back into a number of minutes? I like it. So I can use this formula. Negative 1.08. Kick ass. Kick ass, right? And then you can solve for x. Normally I would put the x-score there and figure out what the z-score is, but now, of course, what I know is reversed. I'm hoping some of you are like, there's a better way, Jack. And some of you, of course, are always like, there must be a better way. Tell me which button to press to do this problem. But I'll get there in a minute. This is not the best formula to use for this case. We have to kind of create a new formula based off of this dude that would be better to use in this case. But what do you get when you try to solve this for x? You're doing a lot of algebra that you really shouldn't have to do. But if you try to solve that for x, has anybody done that yet?
I'm almost done too.
23.2.
Yes. 23.21 minutes? Okay, cool. So let's talk for a minute about a better formula than this. And the extra bonus of the better formula we're about to create is that I don't allow you to have notes, but the formula we're about to create is a note, if you let it be. So there's nothing I can say about it. It's a formula. You're allowed to have those. What the hell do I mean? I don't know yet. Let's talk about it. Okay. So if I take that, this is a really nice example of why in algebra you work with equations that don't have any numbers in them, because you desperately have to be able to do that. Because this is a good formula if I know x and mu and sigma, but it's not a good formula if I know z and mu and sigma. So instead of solving for x every damn time I have a problem like that, and that adds up over time, and the first thing that comes to my mind, I know a lot of you guys are not going to become computer scientists or even programmers, but a computer programmer would not want the computer to do that 18 million times to have to solve it. He wants to have it solve it once and then just get the answer, and that's a lot of time savings. So if it's Microsoft programming, it's stupid, it's operating system, and like, why does it take so long to boot up? It's because some idiot programmer didn't do something simple to make the code more efficient. So instead of having to solve for x a million times, let's solve for it once, right now. How do I solve for x? Beautiful. The worst part about this equation is it's divided by something weird, so let me multiply by that thing.
both sides. Bam, bam. So I get Z sigma equals X minus the mu.
Add you.
Add mu. Kick ass. All right. Now watch this. You ready? So what's one question that will be on every test from here on out? Do you guys remember? I'm going to ask you, what does the Z-score tell you? Right?
Every test.
Yes, like I said before. This tells you what it tells you. It's the number of standard deviations. Does that make sense? If Z were 3, that would be 3 of these, wouldn't it? So Z is the number of standard deviations from the mean to the data point. Holy shit. So like any equation, that is a sentence. It just happens to be written right now in the mathematical language. So now you know how to translate that damn thing. So now there's even less of a reason for you to make a mistake on the question. Unfortunately, I still won't get 100% right, because I always say this, and it still doesn't help everybody. But that tells you exactly what it is. That's a Z-score is the number of these from here to there. That's what it tells you. All right. Sweet. So any questions from that handout? We did part of it last time and part of it this time. Is that decent? Yeah.
Yeah, can you put the paper that you have there to see that graph from the last? Yeah, thanks.
Okay, so let me give you a problem that uses this one directly. So we know that IQ scores are normally distributed. Sort of a cheat because we actually force them to be, but oh well. That means we really, really know they're normally distributed. If you happen to know your IQ score, you know where you fall. If you have an IQ score of 100, you're right on the average, right? To get into groups like Mensa, anybody ever heard of Mensa? Mensa is the really smart people, I guess they gather and eat donuts. I don't know what they do. Solve Sudoku, I don't know. You have to have an IQ score of 133. 133 would be about how many standard deviations up from 100? A little more than 2 standard deviations up from 100. Would that be an unusual IQ score to have? Yes. So you see why they kind of maybe set it around there, because they want the top whatever percent to be in their group, right? How are we doing so far? So my question to you is, let me ask you 2 questions. Find the probability that somebody has an IQ score above 133. Find the IQ score for the top. Well, let's say this for P20. So do those 2. If you didn't get a Z-score chart, it's in the book. If you don't have a book, you're surrounded by people with Z-score charts. Some of them have to be friendly.
All right, let me try to start catching up to you guys. What's the first step on this problem here? Yeah, find the z-score. If I can find the z-score, I can look up at the chart, get that. I can adjust it to be above. So how do you get this to be a z-score? All right, cool. And then 33 divided by 15. 2.2, I like it. If you look up 2.20 in the chart, I get 9861. So that's this area here. So what's up here? 139, yeah. So about 1.4% roughly of the population would be eligible to become members of Mensa. How could Mensa use that information? I mean, they could use it in their advertising for the other one, or the top one. But here's the thing. If they wanted to open up a new little group in a city, let's say that they want to open up a group in a city with a population of, what you got, Jeff? 950,000 people. What would they estimate the number of people who would be eligible to join their group would be? Yeah, what percentage of the general population is eligible? 1.4%. So if there's a city of 950,000, how could they quickly get an estimate for how many people should be eligible to become a member? Yeah, 1.4%. So 0.014 times 950,000. So what would that be?
13,300.
About 13,000 something? Now, of course, you understand, 1.4% would be across all of America. Now, let me give you this example. There's a certain probability that you will be eaten by a shark. There is. It's not zero, right? So when you watch Jaws, all right, but there's a probability that you'll be struck on the head by a meteorite at the same time that you win the lottery and you're watching somebody else get struck by lightning. That is not zero. So just the fact that it's not zero doesn't mean, no. But my point with this is, doesn't mean that everybody has an equal chance. If you go surfing a lot, your individual probability of getting eaten by a shark is probably higher than the little old woman who lives in Oklahoma City, who's never seen the ocean and thinks it's a fairy tale, right? It sounds sort of like my grandma. She's like, "Did you burn yourself, Jeff? Just put some butter on there." I'm like, "Grandma, don't eat me. What are you trying to do to me?" She's funny. She's like, "The dinosaurs never existed. They just put the bones back together wrong." I love her too. She was awesome to talk to. Anyway, sorry. But do you see that's an immediate use of this data. Now, I don't know if anybody noticed I was measuring the door, so that's coming up here in a second. All right. What about the second part of this question? So this problem was done at this point. This is just me doing extra stuff. If anybody out there is like, "How did you get 950,000? No, you wouldn't have to do that. I made that up. Right? This is Jeffsville. How do I do this second part? P20. Where would that line go for P20? Yeah, it's got to be down here because this would be P what? That would be P50, right? And this is 100 in the middle, which is 0 as a z-score. So where would the 0.20 go for the 20%? Above. That's an area. So this area here is the 20% below. Right? So now we're getting into like Forrest Gump territory. Maybe. I don't know if you remember. Your child is here. But I want to. Sorry. I'm sorry. Strike that for the record. So how do I figure out what this z-score is going to be? Yeah, look up the 0.20. Kick ass. So, and you just get as close as you can. Oh, I'm going to dislodge something from this. 0.20, so it's obviously back in the negative z-scores. And the closest I can get to 0.20, what you get? What's the closest you can get there?
Negative 180.
Yeah, the closest I get is 0.2005, right? And this is not the Price is Right. It's just straight up the closest you can get. So if this would have been 0.1998, this would have won. Does that make sense? Right now, this is like 23 away, whereas this is 5 away. Do you guys understand when I say that, what I mean? That's 5 away from being 2000, which would be 20%. And that 1977 is 23 away from being 2000. So that this guy wins. Or you just cut the difference. So this would be negative 0.8, what did you say? 4, okay. So this z-score is negative, let me make this bigger. Negative 0.84. That's the z-score for this, but I want to know what the hell the IQ score is for that. And of course, we've got a beautiful formula now that does that. That's its only job, besides being a note for you. So now you just fill it in. The mean is 100. Plus, sort of, it doesn't matter how you look at this, the z-score itself is negative. So it only makes sense going into this, you know if your answer comes out to be 107 or something, you know it's wrong. Because it should be below the mean. So just somewhere here is going to be a minus sign. Times the standard deviation of 15. So what do you get?
87.
87.4? Okay. So if your IQ score, maybe minus, IQ. If your IQ score is below an 87.4, you're in the 20th percentile of IQ scores, right? Cool. Okay. You can start your own group if you want to. All right. So now, that's section 6.2 and 6.3. And let me say this just to prep you for where we're going. And I want to do the door thing. 6.2 and 6.3 is what I'm going to now refer to as a classic z-score situation. Normal z-score situation. Because what we're going to do is we're going to start looking at situations where things get tweaked a little bit. 6.4.6.5 is the first tweak we're going to make. So the whole process will be basically the same. There'll just be one little thing we got to change. And I said this on the first day, and I'm not saying this to make you scared or any kind of shit. The only thing that people have trouble with in this class is really, when do I change the formulas around based on the situation I'm in? So you just have to really know. And I try to teach it with the concept, and then I tell you, here's the triggers. These two things mean do this. Right? But I want you to understand why it means that. Before I get too far away, let's do the door thing again. Let's do the door thing. I think we all agree that men are on average taller than women, right? At least in our culture, in America. It's actually not true everywhere. The mean height of men, I think the book, actually I looked this up, it's like 69 and a half now, with the standard deviation of let's just say 2.5 still. I don't think that would have changed.
Who's the height of the board?
Men, yeah. So what I'm trying to do is, I'm trying to say, how should I design a door so that fewer than, I don't know, you're the designers. I obviously want fewer than half the men to have to duck. But we probably want to do better than that, right? How tall should this door be so that fewer than what? You guys tell me. Fewer than what percentage of men? 5%. Okay, you're like, screw the 5% of dudes who are tall, screw them. They should just expect this to happen. So,
You know, I have a friend that's 6'10".
all right, cool. So when he walks in our door, he better duck. All right. So I'm doing the work for you. What am I doing? Sorry. So I want to know, I want to say, how tall should the door be? How tall should this door be? And actually, we can even extend it to ceilings, right? I can make the door as tall. Like, we don't have that much room. We can't do a really tall ceiling, but I want less than 5% of men to have to duck. So how tall should the doorway be? So that less than 5% of men will have to duck. Or, just go ahead and get
conked in the head. It's up to them. Right? And then there'll be a little erosion thing where there's a little indentation on the side of the door. All right, so I kind of started this off already. What is it that I'm given? Am I given a raw score or am I given a percentage? Obviously, I'm given a percentage. So, and I want less than 5% to have to duck. Unfortunately, I already gave this away too, but why did I start drawing things where I did? Because do they have to be short or tall in order to be affected by this mandate? Tall. So I want only these people to be too tall. I want this to be where my door is. Its height of my door, I want it to have 95% of the people should fit through just fine. These top 5% of, as far as height goes, will have a problem. All right, how are we doing so far? And this is a real problem, this kind of thing. Or how wide do we make airplane seats, right? We keep changing. Well, now what is the hip size of the average American? Right? So this would be what? What percentage? That's crazy. And then how do I figure out this, what I need here? Yeah, good. I love it. So this is above, so I got to get below because the chart only understands areas that are below. So if I try to find 0.95, something went wrong.
It's 1.645.
Beautiful. It'll be that. We saw that before. It's that asterisk place, right? What's the closest you can get to 95%? Right in the middle. So if you follow that view down, it's right between 1.64 and 1.65, so it's 1.645. It splits the difference. So this z-score here is 1.645. How do I figure out the height of the door then? Yeah, plug it into our beautiful little formula here. That x equals the mean plus the z-score times standard deviation. Let's see what you get. It's like 74. It's a lot of typing. Has anybody got an answer for me? 73.6? All right. Which is like 6'1", really, right? So the 5%, we expect to get 5% of complaints maybe, right? So we can control that though, right? We can control. We might go, let's change that to 1%, we'll redo this thing, right? The door is actually 79 inches tall, so they were like, we don't want anybody to complain. These students can't withstand hits to their head. They're having enough trouble with stats as it is. We don't want to add brain injury to that. So they made this door really damn tall. So another question I could ask you is, what percentage of people would be taller than 79 inches? And then that would be a straight up normal z-score process, right? Make that into a z-score, look it up, do 1 minus the area you get. Be a very small percentage up there. So they were really being careful. Yeah.
I get like how to find a score on the chart, but how did you know you just didn't do like 0.95 and not like 0.05? Like I know it's not on there.
The chart only understands areas that are where. Exactly.
Okay.
So the chart will only give you areas below this, so it only understands areas below. Now, if you did look up 0.05, you would just get negative 1.645. So then you just take the negative off because you know it's up there. So there's that symmetry thing again, where if you realize what's going on, it won't freak you out. Otherwise, your door is like this, and you're like, what's the complaint? We did all the work. Just get down, crawl. All right. So the rest of the class I want to focus on 6.4 and 6.5. So to get us into the idea of 6.4 and 6.5, let's do a quick problem based on what I got up here already. And you guys help me really interpret what's going on. So given this, what's the probability we pick a dude who is taller than 68 inches, who's more than 5'8"? So do that real quick. You can't do enough of these problems, so one more of these is good. So I really want this process just to become like almost automatic. It's always the same. I just change the numbers. One thing I left out up here, but we've already talked about heights. What's true about heights that allows me to use the z-score chart? What has to be true before I can use that chart? Beautiful. It's got to be normal. Well, we've already said before in this class that heights are known to be normally distributed. Right? They just naturally happen that way. Nobody's out there making it normal. Well, you're not quite right. So, of course, what's the steps here? The steps are almost always the same. They gave me a raw score. Good. Change 68 to a z-score. 68 minus 69.5 divided by 2.5. And you get negative 0.6. Okay. Yes, go on. So this is 0. This is negative 0.6 for z-scores. And then when you look up negative 0.6, you get... What do you get? 2743. Sweet. And of course, then the actual area that I need. 7257. Cool. All right. Now, everybody take a second, write down a sentence that exactly tells me what that means. Don't say it out loud. Just write a sentence down that tells me exactly what this means. You can change it to percentage if you want to, whatever you need. Don't tell me it means 7 is in the tens place. Physically what it means. Alright. Who's got a good one? Who's got one? You guys are all writing something. Who's got one they want to share?
72% of men are taller than 68 inches.
Right. So you could say that, like almost 73, so somewhere in between it, so 72.5% of men are taller than 68 inches. All right. Anybody else say it a different way? You could also say there's a 72.6% chance that you'll randomly pick a dude who's taller than 5'8". Right? Did somebody else write that? Beautiful. They're both the same. Right? Because if 20% of the people in here own a Hyundai, that means that there's a 20% chance that I'll pick somebody who owns a Hyundai if I pick somebody randomly. You with me? They mean the same thing. Sweet. Huh? Hyundai? Cool. All right. So, the difference between this and actually what most of statistics really is if I want to test the effectiveness of a drug, let's say I want to test to see if it makes people grow taller, right? Safely, instead of some human growth hormone or something. If I want to test the effectiveness of medicine, am I going to say, I'm going to test one person and see, will I do that? Will that be good? Will people read that and say, oh, good, he's done well? No, of course, what are we going to do? Yeah, we're going to get a large sample of men or whoever, women, whoever wants to be taller, right? We'll include dogs. We don't want to taller. So this is not really what we're going to need to be able to do more advanced studies. This is the probability of an individual dude being taller than 68. I'm going to have to know the probability of a group of people to be taller than 68 possibly. I need to be able to do this with samples, not individuals. So everything we've done so far has been about picking a person, picking somebody who parks at Grossmont, picking a card, picking the... I haven't talked about picking samples of things and looking at that yet. We sorted it with binomial probabilities, but that's not normal distribution. That's what I'm talking about. What do we do with normal distributions to be able to do that? So things are going to change a little bit. So I'm going to go through some concept work, right? Which means I'm going to show you where things come from. I want to tell you this right now. The amount that changes here, one number up here changes in a formula that has 1, 2, 3 variables in it. Right? That's it. That's the only change. It's going to take me a little while to explain why. And we're going to even do some interesting stuff. But then at the end result will be this formula will have one of these numbers will be a little bit different. That will be the only change. Right? Some of you guys are like, just tell me that, man. Too bad. I'm going to put you through it. It's too bad. You're here to learn. I don't care if that's actually what your intention is. It's going to happen. So what I'm going to do is my own standby, because I just like this example. And I think I've used this once before when we're talking about chubby dude. If we go back to that Florida that has a bunch of young people and a bunch of old people, right? And the mean is like right there. Do you remember we talked about this before? And then God came down and said, you all get younger and you all get older. And the standard deviation grew to catch it. And that's why chubby dude's theorem works, right? Do you kind of remember that? Or Chevy said, I should be a little more respectful. You did some good work, right? Probably wasn't chubby either. It wasn't much food bag. No McDonald's. So this is a plot. Now, how was this plot created? Besides me just if somebody actually did this and this is real, how would they create this plot? How would they make this? What would you go do? And again, this was ages of people in this alternate reality Florida. What did this person do to actually create this? How did he know that there's nobody in here that's aged in there? What did he go do? No, he did better than that. He went to all of Florida, right? I didn't say this was a sample, did I? So he talked to everybody in Florida. In fact, what symbol did I use here? Population mean. All right, cool. So he talked to every person in Florida, right? This guy, he was independently wealthy, so he had plenty of time just to walk around. And he would check people off like the people do on your tire to make sure if you're there for 2 hours. But it wouldn't come off. All right, you guys aren't with me. It's okay. Just make sure you talk to them already or not. Indelible ink, maybe, like they use in countries to see if you've voted already. And you guys are all like, what the hell tangent is he going? All right, coming back down. I'm sorry. Coming back. What this person would have done is he would have said, how old are you? I'm 97. Okay, then he puts a point there. How old are you? I'm 3.5.
So then he puts a 3.5, a point there. You kind of with me? So what ended up, he keeps doing that. How old are you? Bam. How old are you? Bam. How old are you? Bam. There's a lot of freaking people. So this is this tall because there were a lot of people that were that age, of course, right? We're kind of used to this. Why is the tallest bar in a histogram? Because that's where most of the freaking people were, right? We know that already. But I just really want to make a point out of how this would have been created. Taking individual people and plotting them on this. Is that cool? Now, of course, what we just said was, let's do this again. But let's use something that's more like what we do in most statistics, which is taking samples. So now for the next 10 years of his life, he's going to go around and take samples of 10 people at a time. So he's not going to say, how tall are you? He's going to say, you 10 people. How tall are each of you? And then he's going to average them out. And then he's going to plot that. He's going to make a new graph. But can you guys make any predictions as to what's going to happen in this new graph? So in this old graph, this is individuals. How tall are you? How tall are you? How tall are you? How tall are you? So there's all kinds of all over the place. If I take 10 people at a time, what's the most likely thing that's going to happen? Be less, let me see how to say. So is it likely that I'm going to pick a bunch of people who are 1 year old? No. What's the most likely thing I'm going to get if I randomly pick 10 people at a time? So is it likely I'd get all these people? No. So the most likely thing is I'm going to get a mixture. So their average age, the most likely average age of all the groups of 10 I'm picking will end up being what? If I said the average age of Grossmont is 27, and then I go pick 10 students, what's your best guess about their average age? 27. Right? Because any sample, if it truly is randomly picked, should represent the population. Now, does it have to necessarily be 27? No, that's why this picture's not going to have a line at the mean saying everybody was the same. No. But what's the most likely thing, what's the one I would put money on, is that it's close to the real mean of the whole population. So before, was there any individuals in here? No. But now, the weird thing is, the highest point will be over this dude, because now I'm not plotting individuals, I'm plotting means of groups of people. That is the fundamental difference between this distribution and what's called the sampling distribution. Key thing that students just have a lot of trouble with, and I don't blame you because it's weird. And it's weird because it's getting really close to what we do in real life, and that's always harder to understand because real life is weird as hell. So, there's nobody here. Nobody is exactly in between. Do I talk about age or height? Nobody's exactly in between here as far as age goes, right? It just happens to be that way. But now when I take my group, now the tallest peak is going to be right here. Now the next most likely thing to happen is a lot of people in here, because these are two really tall peaks, right? So if I pick 10 people, it'll probably look something like that. Those peaks corresponding, well, let's see if I can make this a little more. All right. So those peaks corresponding to these peaks, right? They shouldn't be as tall. All right, Jeff, just leave it. They get the idea, man. All right. Now here's the important part. That's really funky. Whatever this standard deviation was, what is it now? How is it related to this? Which one of these has a bigger standard deviation? Which one has more data points further from the mean? The top one. So this is the bigger standard deviation, right? So this standard deviation for this guy has gotten smaller because all of the data is starting to rush to the middle. Cool. So this, I'm going to denote this. Actually, this even too, both of these. This is the standard deviation of what? And this is the mean of what? When I plot a point, be very specific, what does that point represent? Ages of what? Groups. Hey, all right. It's the mean age of a group of size 10, to be really specific. Sorry, I didn't mean. So this is the mean of, so every single dot is a mean itself. I take a sample of 10, I get their mean, I plot that. I take a sample of 10, I get their mean, I plot it. So when I average all of those averages, that's what it really is, an average of average. So I actually call this the mean of all the sample means. So this is the standard deviation of all the sample means. It's how the sample means are distributed, because what actually is in this picture, sample means. So it's about how, I don't know why I keep yelling at you. This is how spread out the sample means are, right? How are we feeling so far? I know as a student, whenever you have to suffer through one of these, you're like, what part of this do I have to do? So just hold on, we're not there yet. Right? None of this you would ever have to do yourself. This is weird shit. This is me explaining stuff. Trying to. Do I want to hold on to you? Yeah. So the weird, what's interesting is, so this is for like n equal to 10. If I get n equal to 30, no matter what the distribution looked like before, I'm almost guaranteed this will work for most distributions. If I hit n equal 30, my distribution will suddenly look like that. Something like that. Where this is the old mean. The standard deviation now is really, really tiny. Because now if I pick 30 people randomly, how likely is it that I get 30 90-year-olds? Just randomly. You, and then I'll go about 3 blocks up, and you, and then, holy shit, a bunch of 90-year-olds. No, if I randomly pick people, it should really be a mixture now, right? So it's almost impossible for it to not be a mixture anymore. So that's why it's definitely gotten here. So the standard deviation is even smaller. So as the sample size goes up, the standard deviation gets smaller. Yes, good. Because everybody is rushing to the middle, right? So let me give you a little more concrete of a situation. If you were to go out, if I asked you, go out and randomly pick somebody, would you say you have a decent chance of picking somebody who is 5'5"? Decent chance. There's a lot of women who are 5'5". There's a decent number of men who are 5'5". You have a good chance, right? Pick somebody 5'5". What about picking somebody who's 6'3"? Not as good, but still, it could be done. If you go randomly pick somebody, you still have not a crazy chance. Now, listen, so 6'3", we could do the whole work for that, but let's say it's like a 10% chance that you'll get somebody who's at least that tall. Now I ask you to go randomly pick 30 people, and I want their average height to be 6'3". Is that easier or harder?
Harder.
It's much less likely, right? So if the original picture for heights looks like this, so here's like 63 inches tall, so there's a decent probability of getting out there. This is for individuals. If I now pick a sample of size 30, and I've left myself no room for this. If I pick a sample of size 30, the picture now looks like that. And here's 63. There's like nobody out there. Because, and that's not saying that there's nobody who's taller than that. That's saying that, why is that such a big deal, Jeff? I think you meant to say 73, but that's all right. That's great. But it's just saying that now it's going to be closer to the mean. Right? Yeah, I think I did mean 73. I wanted this to be a crazy number. Did I say 6'3"?
Yeah.
All right, good. That's even better. So that would be, you can do it, Jeff. 75 inches tall. So that's difficult in itself, but it becomes even more difficult if I'm asking you to do it for a group of size 30. So now we're shifting our attention to doing a lot of the statistics work we're going to do is going to look the same. I just got to make an adjustment if it's a group I'm talking about. So the probability for an individual to be out here is not crazy, but for a group of size 30 to be out there, their average to be out there, that's getting kind of crazy. Because now I really expect people to be here. How we doing? Okay, cool. Maybe. So, let's get a little bit closer to something you'll actually have to do yourself. So everybody got this here? trying to hold on to this dude because I want to do something with it. Well, I could do a different one. Let's see. So, I don't want to work with a population as large as Florida. I don't think we have enough time for that. So, let's say that in a hat, somebody help me out. Give me some numbers here. From 0 to 10. Some numbers. 6. 8. 7. And 2. Hey, look at that. It's crazy. All right. So we'll use 4 numbers. Right. I got a little handout that's going to capture a lot of what we're about to do. But I want to kind of do it before I give you this handout. Take a second. Can you use 1 bar stats if you have a calculator? Just figure out, and you don't really need it for the average, but you want it for the standard deviation, so might as well go and do it all. Figure out what the mean and the standard deviation is. This, by the way, is my population. We're pretending like this is Florida to be related to that, right? That's a population. Actually, I want to point out something. Should be getting this, right? Yep. So the mean is 5.75. The standard deviation is 2.278. I'm using that one because it's a population, right? Notice something very interesting from the very beginning of this. When I said it, this is true, but there's also another way to look at this. This is SX because I only had 1 variable, so if there were 2, there would be SY further down. Does that make sense by itself? That's why the calculator puts a little X there. But, you see the little X there? SX. Is that cool? Alright. Another way to look at it is, this is not SX bar because it's individuals I put in there. So this is the standard deviation for individuals. Right? Not SX bar, it's SX, or sigma X, not sigma X bar, because I put individual scores in there. Does that make sense? I like that. That's what it gives me. It's not really why it does, but I just like to say it. So this is like mu x and sigma x. This is for individuals, like we've always done. Now, help me real quick. If I reach in there and I start taking samples of size 2 with replacement, so nothing weird happens with my probabilities. We all understand now if I did it without replacement, my probabilities all change. Screw that. Let me do it with replacement. Can somebody help me construct a nice orderly listing of all the possible samples of size 2 that can come out here? So maybe start with the lowest and go up. So, for example, I could get the number 2 twice. So I could get 2, 2. Or I could get 2. So reaching into my hat and I'm picking out 2, throwing it back in, get 2. Or I could get 2 and then I could get 6. Hey, look at that. Then we can be organized about it. So, or I could get 2, 7. Or 2, 8. So that's all the ones with 2 first. All right, so then we can just do the same thing now, but we'll have 6 first now, right? So that'll be 6, 2. Leave some room here. 6, 2, 6, 6, 6, 7, 6, 8. 7, 2, 7, 6, 7, 7, 7, 8. For real, Jeff? Yeah. 8, 2, 8, 6, 8, 7, 8, 8. Those are all the possible samples of size 2 that could occur, right? So just imagine if I try to do this with Florida, millions of people in Florida, I'm picking samples of size 10 for that situation. How long would that list be? I am not even going to think about it. Right? So this is a nice, small, concrete. We're 6'4", you've got to do this. Let me make this clear. This is no longer me showing you derivations. This is actually something you got to do in section 6.4. This is what your homework is going to look like. And let this be nice. If you haven't been looking at exercises or stuff, they give you the freaking list you have to use already created in the example in the section. So a really good idea to read the book. So what we're going to do now is exactly what I said earlier. I went to Florida, I picked 10 people, and then I took, that's right, I took a group of 10, and then I did what with their ages? Found the mean. So I'm going to find the mean, and it's a sample mean now, right? Because this is just a sample from my population. I'm going to find all the sample means. So what's the mean of 2, 2? 2, that's great. When you average 2 and 2, you get 2. Whoa. And when you average 2 and 6, you get 4. It's no way. 2 and 7, 4.5. I love it, right? 2 plus 7 is 9, divided by 2 is 4.5. 2 and 8, 5. Kick ass. 6 and 2, we already did. See that? 6 and 6. No, 6 and 7.
6.5.
6 and 8.
7.
7 and 2.
4.5.
4.5. 7 and 6, we did already.
6.5.
7 and 7 is 7. 7 and 8.
0.5.
Thank you. And then 8 and 2.
5.
8 and 6. 8 and 7.
7.5.
8 and 8. So on an example with Florida, I had the individuals kind of graphed. So if I graphed these, that would be really boring. Here's 2, 6, 7, 8. How tall would each bar be? It's not really a histogram because I don't have a nice scale, so I can have gaps. But how tall would each of those bars be? If there's 4 of them, what's the probability I get any one of them? 1 out of 4. So they're 1/4 tall. So the total area of those bars, if this is 1 wide, the total area would be 1, like it's supposed to be. You guys semi with me? A little tiny bit. All right. Maybe. So now, that's the individuals plotted. Now I'm going to look at these. These are like my new data points for my sampling distribution. These are the new data points. I created them from the population.
Why are they 4 tall? Like, why are they 4 tall?
Oh, how do I say? So because of the fact that the first guy could be a 2, and the second guy could be one of 4 things. So there's going to be 4 things that have a 2 first, 4 things that have a 6 first, so forth. Yeah. How many options are there for each of those numbers? There's 4 times 4 is 16, so there's a total of 16 averages, right? So it makes sense to make 4 by 4. Yeah, cool. A few different reasons. Whew. So, do me this favor. While I'm doing something weird up here, can you guys plug these into list 1 and find the mean and the standard deviation? Somebody's doing that, being very mean to us, but you guys made the numbers up, not me. 2, 4, 6, 8, 10, 16. Looks like I got everybody. So you guys got the mean and standard deviation for all those numbers? You guys, anybody have that yet? Anybody want to share?
5.75
Is the that's wait, yeah, good. All right, that's good. Forgot what it was. So mu sub x bar is 5.75. And real quick, if I took everybody's age individually and then calculated the average, would it come out any different if I took two of you at a time and then calculated the average? Would it come out? Of course not. It's the same stupid numbers, right? Okay, good. So always mu sub x bar has to equal mu. The center doesn't move. It's just that the standard deviation should now be smaller than it was before. What do you guys get for sigma now?
1.61
1.61
05.
05. Okay, 1.611. All right. You okay?
Yeah.
You good? Okay, cool. How big of a sample did we take?
40.
So we took, how many samples did we take? We say it like that first. How many samples did we take? 16. How big was each sample? Yeah, each sample was how big? 2. Right, we took a number and then we picked another number. So our sample size was 2, and we repeated that until we got everything. So the guy walking through Florida, he's got to take every possible sample of size 10, and he can't stop until he's done. Right? So that's why I didn't want to do that. So it's only a sample size 2. This doesn't look normal really at all, but if you had to say which one of these looks more normal, which one would you say looks more normal? If somebody had told you, you must tell me which one looks more normal, this one does. Starts low and eventually goes high and then goes low real fast, but it's starting to look more normal already, barely. But again, we only took a sample of size 2. Once you get to 30, that's the magic number. Once you get to 30, I don't care what your distribution looked like to begin with, it's going to look normal at 30. And again, what's a big part of statistics is I want to be able to use that chart that I've taken away. I want to be able to use that chart, and I can't use that chart unless I have a normal distribution. So if I'm using a sampling distribution where the sample size is at least 30, it's normal enough. Maybe not. All right. Now the other thing, now watch this. Take the old standard deviation, sigma, divided by the square root of n, which is the sample size. Now we know the standard deviation gets smaller. I'm claiming that it gets exactly smaller like this. I can't prove this to you. It's a little bit beyond the math level that most of us are at. But what is the old standard deviation? 2.278. And what is n? I tried to make this point just a second ago. What's n?
4.
Say it one more time.
4.
How big of a sample did I take?
16.
No, that's how many samples I took.
Oh.
How
2.
big was each? Yes, 2. Good. So 2, that's the samples, right? How many times did I have to take a sample of size 2? 16 times. See, they're not the same thing, right? Every sample I took is too big. Not too big, but too big. So what is 2.278 divided by the square root of 2? Huh?
Why is it the same?
Because the new standard deviation, the standard deviation that represents your samples, will always be the old standard deviation divided by square root of n. So this is the standard deviation that is good for groups of size 2. Now I want you to realize, how did we get this standard deviation? We had to make this and then plug it in the calculator, right? Right? Can you imagine, even if I just kept these 4 numbers, but I made you pick 3 at a time, sample size of 3, what would happen to how big this is? Because it would get a decent size bigger, right? Shit!
it would be not 4 times 4, it would be 4 times 4 times 4. So now we're talking it would be 64. If that's the only way that we had to get this, I doubt we would do it. Right? So thank God, this formula does the same thing. Directly take the standard deviation of the population of individuals divided by how many people you're taking at a time, square root. It's the standard deviation of the groups. It's how spread out the groups' ages are. And the group's ages, of course, will never be as spread out. That's why the formula gets smaller. It's divided by the square root of n. It gets smaller and smaller. The bigger my sample gets, right? It'll get smaller. It'll get closer to the middle. Whew. Now I told you. Now we're going to do a concrete example, and then we're going to head out. I told you it's going to take me forever. And you guys are like, it always does. So why was that special? You always talk a lot, Jeff, and you make this much sense. I'm like, shit, I tried. I'm desperately hopeful that you guys got something. And I got a little handout. Let me go ahead and give this. Well, I'll give this to you right before you leave. I want to show you how this is going to affect you immediately. All right, so let's go back to IQ scores, I think. Mean was 100, standard deviation was 15. And the book does exactly like this. This is 6'4". This here is 6'4". What we're about to do is 6'5". 6'4" is the concept and constructing these little tables and doing stuff. The idea behind why this is true and all that kind of stuff. 6'5" is just use that. So 6'5" will be much easier than 6'4". Don't skip 6'4". It's bad. So let's see. Part 1 is probability. Pick one person. What's the probability that their IQ is, what you got, Jeff? Less than 90. And the second part is pick 20 people. What's probably that their average score, their mean IQ score, is less than 90. So let's do this together. Sound like math church, right? So let's do this together. What goes right in the middle? 100. So part 1 is the easy part. That's the classic traditional z-score problem. I mean, not say easy yet, because it's still relatively new to us, but it will become the easy part, right? Here's 90. I want less than. That's awesome. I then immediately do what? To find this area, I have to get a z-score. Very recipe-ish, this is. Please